Okay, so we were here. Um, so I can see my LED blinking. So this code runs successfully. If I pause this on the left side, you get the call stack. So I'm in main.c. I'm actually here and waiting in the HAL delay function, which is called from the main. So you get the call stack here. All right. So we have the first method done, how we generate code with the CubeMX, but I don't use it often. Uh, what I prefer is directly import some examples and then start working from there. So if the ST also provides a different kind of examples for each peripherals, and you can just directly import those examples and start working on it. And you can use CubeMX as a side kick. If you want to configure, if you don't know how to configure a peripheral, you can just configure that particular peripheral, generate the code, and that copy that code in your main project, whatever you are working on. So you can use CubeMX like that. I will show you how to import a example project and then start working on it.
So our boards are specifically in an import mode initially, right? We need to configure it as output and then only it will work, right?
Initially, all the GPIOs are in analog mode because that consumes the least power. We need to put it in output mode if you want to drive the LED, or for example, in alternate function mode, if you want to configure the LED as a UART pin. So if so different peripherals, for example, in case of UART, you need two pins, use are TX and RX. So the pin, any GPIO pin can have input, can take input from the outer space, or can drive output on it, or it can be in an alternate function mode. So there in for each pin there are some alternate functions defined specifically, that is defined in the data sheet. So there is an alternate function mapping list. I will show you in some time. So there it is mentioned, okay, this pin can have these alternate functionalities. It can be used as a user TX pin as well. So if you want to use it as a user TX pin, you need to put it in the alternate function mode. So different modes you can use for each GPIO pin that we have.
Okay. So like, as we're talking about LED, right? There is this open drain, then there is push-pull mode, right? Can you just
Hmm.
highlight what exactly PMOS and NMOS circuit would be on and off? And secondly, when you're connecting an LED or a switch, what is the need of connecting a pull-up or pull-down resistor in the configuration? As you rightly showed, right? In
Hmm.
our file where there is
Hmm.
pull up, pull down, and output mode, things like this. Can you just throw a light on that also?
Okay. For example, an open drain configuration. In open drain, if you have heard in I2C, we have open drain configuration. So what an open drain configuration is, you can drive the signal low, but it will be pulled automatically up by an pull-up resistor. So pull-up resistor is nothing but a resistor connected to a high voltage, the high value, the VDD. So it is connected for your output, and you can drive. And I don't remember the specific electronics, the NMOS or PMOS, but you can drive your transistor. So if you give the output to the transistor, it will be on, and it will drive your output as low. So in an open drain functionality, what you can do, you can output it as low, but if you switch off your transistor, then it will be automatically pulled up by the pull-up resistor. But in push-pull configuration, you can both push it high or pull it low. Both configuration you can do. So in case of LED, you want to do both. Uh, you want to make it high and make it low as well. So I am using the push-pull configuration. Maybe Muskan, if you have some more
Yeah, I
points on it.
can like highlight on this. So basically,
Yeah.
there are buffers, output buffer and input buffer. So in order to configure any GPIO pin or port, whatever you want, if you want to drive a lot of LEDs together, you can use a port. Okay. Now there is this output buffer and input buffer. We are using LED now, right? So we need to enable the output buffer. Now you might think, why do we need to use a buffer, right? When we have this whole circuitry there. I mean, why do we need this buffer? Now the thing is, we need to protect our internal circuitry. So there is this GPIO, okay? By own, if you keep the board like this only, nothing will happen. If you power it and maybe connect something and a loose connection is there, something can happen. Okay. Now talking about buffer, we have PMOS and NMOS circuitry. Okay. So the thing is, the signal can reach to the pin and also damage the internal circuitry. We do not want that thing to happen. That's why there's a concept of buffer. Otherwise, why do we need this buffers? A simple wire is there. We are putting zero at the input. We will receive zero at the output. Why do we need it? Reason is this. We do not want the current to damage the internal circuitry. So point number one to be noted. Now coming to the fact, there are various modes like open drain mode and push pull mode. What do you mean by push pull? Push pull means there is a PMOS transistor and MOS transistor which is there connected. In the output mode, it will be like PMOS and MOS transistor connected. There will be a pin over here, and there would be the internal where the signal is going to the inner part of it, telling the processor what is kindly do this kind of thing. Now, push pull mode is a mode where we do not require any pull up resistor or pull down resistor. Okay. Normally we see push pull mode in the output mode, right? And open drain is what do you mean by open drain? Open drain means PMOS is turned off. We need to actually program it when you're going to do a bare metal programming. So PMOS is turned off, only NMOS is active. So according to the signal which we give, there's this NOT gate which is there. We are going to connect it, and then we're going to give an input. Accordingly, the pin will turn on and off. The need of pull up, pull down resistor. There is this three states which we have. First is like on state, then there is which is basically the high state, off state, which is basically the low state, and there is this high Z stage, which is called infinite resistance. Say there is VCC and there is this ground, and between that we are not connecting anything to the pin, right? That is a stage where the if you see a graph, it will turn on and off toggle again and again. It will not give a stabilized output, right? So in order to get a stabilized output, we need to make the pin, basically you need to forcefully put the pin as high or low, so that we'll get only two states, which is understandable. Now in a graph, if you talk about, there is these three regions. Yeah, floating. Yeah, we are very, very much correct, Karthik. Okay, there is this state is known as floating state wherein it is floating between high and low state. So there are three regions, right? Low state and high state, and there is this intermediate stage which is not identifiable, and it makes your voltage unstable, right? So now you were talking about this LED, right? Now we are driving it in which mode? Can you again just open the inner configurations part? Can
Yeah,
you just
LED
share?
is in output push pull mode. Yeah.
Push pull mode. Okay. So
Yeah.
push pull mode we are having right now. So in push pull mode, what is we are having is here we are not configured any internal resistors, the pull up or pull down. Why? Because push pull mode is itself self sufficient, right? How? Now there is this PMOS which helps in making our pin high. How? I'll tell you. And there is this NMOS which helps our pin to be low. Now let us talk about how it is turning on or off. Okay, there's this PMOS which is connected to which source is connected to the VDD, which is the source, and NMOS source is connected to the ground. Now we want to turn our pin high. First, we'll enable. Firstly, we'll enable in the output buffer. We'll enable the output buffer because we want the output thing to happen. Since we're connecting a LED, since we are now using a inbuilt LED in our thing, but it's okay. Now let us talk about how we're turning it on. So we see this VCC, the VDD is there. So when we are going to put the any input to make the PMOS on, now the condition for your this PMOS to be on is the gate voltage should be less than the source voltage. Then only your PMOS is on. When your PMOS is on, the current flows from VCC to the pin, right? It is acting like a pull-up. We do not need any internal pull-up. Now talking about NMOS. When NMOS is on when VG, which is the gate voltage, is more than the source voltage. That is when we are pulling the pin low. So you see, we do not need pull-up, pull-down resistors in this case. Now for safety purpose, this ST people have kept this resistor, which you can see the ranges in the data sheet, maybe, or maybe in the schematic. What actual value of the resistor we have, generally it is between 200 to 500. Okay, you can see that. And that's how we are switching our, LED on and off. Right? Over to you, Sumit. Hello, Sumit. Can you hear me?
Right, Muskan. Sorry, I went to fill up my water bottles.
Okay. Any other questions you're having? Let me know. I hope you got the concept of open drain, push pull, right? Any questions? Okay, I think we are not having any questions. Sumit, you can continue.
Yeah, thank you, Muskan. That was well explained. That's why they don't have questions. So coming to importing of the project, so I can close this project. I can import. So in the import, you want to go for general and then existing projects into workspace. Next, then you need to browse. So I have already browsed it, but I will show you where will you find this. So in your repository, in your user, your name repository, you will find this folder named as STM32 cube, which will have the repository folder. So in this repository folder, all the firmware packages will be downloaded. For example, I have the same F4V 1.27.1 folder as well 1.28. So these are different versions of the firmware that I have. You will have the H7 or L0, any kind of microcontroller that you have. You will get the firmware packages here. You just go to the firmware package, then you go to the projects. You have different boards mentioned here. So I have AF401 Nucleo. So here it is, 32F401RE Nucleo. I'll go to the examples. Let me pick up UART, the UART printf. So you don't need to go any further. You can choose UART and it will recursively find out whatever the cube ID projects that you have. If you want to import all the examples, you just stop here at this level and it will import all the cube ID examples. Open it. So you have it here. Click on finish.
You cannot see the screen. It's totally black.
Okay, I have not shared it. No, I'm sharing it.
Again, share it. Guys, listen. The
Okay.
concept wise, if we talk about HAL and bare metal, it's one and the same. Only difference is we just using APIs here, right? Understanding wise, concept wise, everything is same. We'll be covering the bare metal programming, right? For now, understand why are we connecting it, when are we using it, and why is there a need, right? So Sumit, please go ahead.
Yeah. Are you able to see it now?
Yeah, we're able to see the screen.
Okay. So I have the UART project imported. So what do I have here? So for each example, you will get a README file. So you can, read it in order to know what the example does. You have a boot support package, BSP, the SIMSYS file, and the hard drivers. And you will have your application code in the user folder. So in the main.c, so UART is configured with its handler. We are using the instance user.x. So user.x is user2. So which user it is? Let me see in my schematic. If I search user.hut, so there it is, user.tx, user.rx. So if I come to this page, you can see, I can see my ST link. So there is an ST link present on your board, and the ST link also have a serial to USB converter on board. So you can use that ST link serial to USB converter in order to have your logs, on the screen, on your computer screen. Otherwise, you need to use a USB to TTL converter, but it's not required if you're using the ST board. The ST link that have is does have it. So you can see the user TX is connected to use ST link RX, and its RX is connected to ST link TX. So which GPIO pin it is connected to? Let me check. So the user TX is connected to PA2 and user RX is connected to PA3. But which instance of the user it is, I don't know. So I have the data sheet here. So in the data sheet, if you go to this section, the pin out and pin description section, there is an alternate function mapping table. So in this table, you can see what alternate functionalities we have for each pin in the GPIO. So the pins we identified were PA2 and PA3. So let me go to PA2 and PA3 pin. So in PA2, you can see it can be configured for as a timer 2 channel 3, timer 5 channel 3, timer 9 channel 1, and as a user 2 transmitter. So we know this pin, we can configure it as a user 2 transmitter. So we want to keep that in mind. And the PA3 can be configured as user to RX. So coming to back to our code, the user instance that we want to use is user2. So these are different instances. Instances is replicas, copies. These are different copies of the user peripherals. We want different number of peripherals of the same IP user 1, 2, 3, so that we can use it for different functionalities. So we are using the second instance of the user. These are some macros I defined. So this will enable the user to clock. Since they were connected to PA2 and PA3, I want to enable I'm just defining the clocks for this, the RX pin. The RX pin is connected to A port. The X pin is also connected to A port. These are some macros for force reset and release reset. Force reset is a macro in which it will give you the state of the peripheral just like it was power reset. So it will reset all the registers. This will use in the deinitialization phase. So the TX pin is pin 2. So we have PA2 pin that is configured as TX, and we have PA3 pin that is configured as RS. And we also want to know the which alternate functionality, the alternate functionality number that the GPIO has. So the alternate functionality number is here. So alternate functionality 7. So the alternate functionality 7 is for PA1 and PA2 is user functionality. So for both of them, it is user alternate functionality 7. If it were different, then we can mention alternate functionality 6, 5, whatever is present in the datasheet. We need to refer datasheet for it. Okay, coming to main.c. After configuring the UART, I am setting the baud rate as 9600, the word length 8, stop bit 1, no parity, no hardware control, oversampling. All these parameters we set for the handler, and we call the UART init function. Then I'm using printf. So printf in turn, it calls a function that is IO putcar for GNU C. The IO putcar function, I am using it, I think here. So here the prototype IO putcar, I am using it to transmit any characters on the UART transmitter pin, TX pin. So I am kind of rerouting my printf to the UART pins. So this is okay. Then
can I interrupt you, Sumit?
Yeah.
So what's the difference between USART and UART? First question. To which bus it is connected to? Because there is high frequency bus and low frequency bus both. So could you show the block diagram and kindly, explain?
Block diagram. Let me.
Is there in the reference manual?
Yeah, let me open it. Okay, reference manual. So the difference between the UART and the USART is nothing but of a clock. So UART is universal asynchronous serial communication, and the USART is synchronous. So what a UART is, you don't give a clock. You only have a transmitter and receiver pins through which you transmit, and the user will also have a clock signal, much like an SPI. I'll show the diagram. Where is the block diagram? Okay, this is the block diagram we have. So let's see. So the user that is present in ST chips have different functionalities attached to it. You can use it as a UART as well. You can use it as a USART as well. You can use IRDA, smart card, all different kind of modes you can use and USART. It is a little, advanced, and you have different types of clocks here. So you have configuration registers, CR1, status registers, through which you configure your UART. You have a BRR register through which you configure your baud rate. So baud rate is something that is, in reference to a UART peripheral, in which if you want to communicate with between two parties, so you want to set up a baud rate. Baud rate means the characters per second or bits per second. You set up a protocol that, okay, I am sending this bits in at this frequency. At the receiver end, you also what is the frequency you are sending in. You set up the frequency, the baud rate at that particular uh, value that you are sending from, and then you can receive the data uh, from transmitter to receiver. So baud rate is calculated through the BRR register here, and you can take a look into how it is calculated. We have the macros defined in our drivers, through which you can give different kind of clock baud rates using those macros. You can just put those values in the BRR register, and that kind of baud rate you can get it. Then what else we have? We have the transmit registers. We have the receiver shift registers. So these are just kind of a shift registers. What we are doing is we are whatever the data we have, we put it in the transmit register, and the shift register it sends that data one bit at a time. So it is serializing the data. So it's called a serial transmitter. Whatever the data that we put here, it will sends ones and zeros on the pen. Any specific question you have, Muskan, on this?
You can basically open the ST's block diagram, the board which you're using, right? And that in there, basically, there's this block diagram which shows buses, the GPRS, how it is connected to it, and how different peripherals are connected to the buses, right? That diagram I was talking about.
I'm not sure which diagram. If you can share your screen, maybe, or you can guide me where I can find that diagram.
I can. You have this open, right? Just search in the initials only. The block diagram might be there. Block diagram. Just search block diagram of the board, STM board, the board which you're using.
Diagram. No, that won't be present in the reference manual for boards. This is the reference manual of the MCU, not the board. Maybe in user manual. If you have it, you can share your screen.
Okay, let me check that out. But now, difference between asynchronous and synchronous. Can you again just throw light on this?
Asynchronous, we don't provide a clock between transmitter and receiver, between the two parties, between which we are trying to establish a communication. We do it asynchronously. Asynchronously means we just put out our data on the transmitter, and the other person need to judge, or we need to give which frequency it needs to sample it. So if the receiver is sampling it more than the should sample it more than the baud rate. Baud rate means the rate at which I am sending the bits. It should sample it more than the baud rate of the transmitter, so that it doesn't miss the zeros and ones that we are sending. In synchronous transmitter, we send a clock with it. So okay, so if I have a edge of this clock on way, and I will be sending it a bit of the data. So the receiver doesn't need to know prior to the transmission that what is the rate at which I'm sending the bits, but it can just follow the clock. So if there is a edge on from low to high, there is a edge on the clock. It will know that okay, now I need to sample the data. uh, it's a bit. So if it samples it high, then it's a one, and if it samples it low, then it's a low. So the receiver
Mhm.
needs to know when to sample. So if we do it through a clock, then that is asynchronous. And if we don't send a clock, we're just sending the bits, then we need to tell the receiver, okay, at this
Mhm.
speed you want to sample it. So that is an
Okay.
asynchronous communication.
So UART is a asynchronous and UZART is a synchronous protocol, right?
Yeah,
Okay. So in
you got that.
asynchronous, we are not using the separate acknowledgement. Uh, Basically, in asynchronous, we are using a separate acknowledgement signal, right? To basically tell we are synchronizing it by sending the start and the stop bits, right? And in case of synchronous, we are just using a shared clock, which itself
Mm-hmm.
telling that acknowledgement signal is sent indirectly
Mm-hmm.
only. And
Mm-hmm.
so we do not need explicit acknowledgement signal basically for sending the next data packet, right?
Yes, that start and stop bit, these are just a way to enclose a packet of data. So if you are uh, sending 8 bits of data, you want to enclose it in a start or stop condition. So yeah, this you need to do it in the asynchronous communication, because the receiver don't know where the data is starting from and when it is ending. And synchronous, you are right. We just use the clock, don't use the start and stop conditions.
Okay, so there is this advanced high performance bus, advanced peripheral bus is there, right? In your
Mhm.
case, this USART peripheral is connected to which bus and what's the frequency?
I need to check. I don't know.
There
We
might be
need
a
to
block
refer the
diagram
reference manual.
of the board. Just scroll up, maybe you can
No,
just search Control F and maybe you can search block diagram. Just block diagram.
block diagram on what, the user
No, no,
chapter
block
or the
diagram
whole
of the
reference?
MCU. All the peripherals connected and all. I guess bus architecture, yeah. He's right. Just scroll down more. Yeah, memory map will also tell you about which peripherals are connected and also tell you about which address is there. Yeah.
Mm,
Block diagram might be there here only. Just maybe scroll.
no. No, these are like
You
block
can
diagram.
search your specific board, STM32 F4REE, right?
You won't find the reference for STM32, I think.
Okay. I'll do one thing. This meeting is going to end. I'll share my screen and show the diagram.
Yeah, maybe you can do that.
Guys, again join.